Okay.
You're number 30, sorry.
All right, so welcome back to calculus. Sure. He's saying in 4.1, he has a question. Number 30. Is that what you said?
Yeah.
Okay.
Sounds easy, but it's just...
Well, again, 4.1 is a good place to be. Let's see. And here's a question 30, he's saying. It's a t over a t plus 3, I think. Is that what I just read?
Yes.
Right. Okay. Again, what's a little funny here on these problems is I'm working on this closed interval. So I'm working from -1 to 6, they say, on this closed interval. And so I'm looking for mins and maxes on a closed interval. So the mins and maxes on a closed interval could be the endpoints of the interval, but they could also be any critical numbers we find that live in that interval. So I need to look for critical numbers, which means I need a derivative. And this derivative involves a quotient rule. Here we go. The derivative. The derivative of the top times the bottom minus, write down the top, take the derivative of the bottom, all over the bottom squared. This is funny. I can already sort of see what's happening, so I just did a quick quotient rule. Hopefully you followed me. It's early on a Monday morning, but it's okay. When I distribute, well, there's nothing much to distribute. If I remove my parentheses and collect the like terms, I think I'm left with a 3. Those t's cancel, do you agree?
Right, that's the derivative.
So this is my derivative. So I could ask you 2 questions now, because I'm looking for critical numbers. So when does this equal 0? And you look at the numerator and you say, when does the numerator equal 0? And the answer is never. Okay. So then the other question is, when is it undefined? It's undefined when the denominator equals 0, which is -3. So maybe for a second I think -3 is a critical number because it's where the derivative is 0 or undefined. So maybe for a second I think -3 is a critical number. But hold on. That official definition of a critical number said, well, it had to be defined in the original function. So if I go back to the original function, -3 is not defined. It's undefined in the original function. So it's really not a critical number. In fact, what is it? I mean, do you know what it is? Again, you kind of got to remember some algebra skills sometimes. When you're undefined in the original function, you could be a hole, but in most cases you're a vertical asymptote, right? So that's what -3 is. It's a vertical asymptote. It ain't a min or a max, or it's not even really technically a critical number. You guys okay? It's that technical part of the definition. Listen, when the derivative is 0 or undefined is what a critical number is, provided it's defined in the original function. So I found what I thought was a critical number, but it's not defined in the original function, so there are no critical numbers. So what was I doing? I was trying to find a min or a max on a closed interval. My candidates are the endpoints of the interval or any critical numbers I find. Well, I didn't find any. So these are my only candidates to check to see who's bigger and who's littler. So now I'm just plugging them into the function to see who might be a min and who might be a max. There are no critical numbers. The only possible thought for a critical number was not a critical number. He was a vertical asymptote. He's undefined in the original function. He's a vertical asymptote. By the way, he's not even in my interval. That's another thing.
Right.
He's not a critical number to begin with. I want to get that argument done.
Pretty sure it was defined in there as well.
Well, right, then he's a critical number.
Because he was undefined on the original, he's not critical.
Right. But also, all right. All right, here I go. So now what do? I plug in -1 in here. That's a -1 over 2. So I think that's -1/2. I plug a 6 in here. That's a 6 over 9. 6 over 9 is 2/3. Well, I think I'll call him a min and him a max. It's weird. Just weird. It's weird working on a closed interval. It's kind of, whatever it is. It's not my favorite problem. You probably could tell that 2 weeks ago when I started this. It's in 4.1. It gets us started. It gets us looking for critical numbers. But this fact that we're working on a closed interval is just not my favorite cup of tea. I want to work on I want to look at the whole function usually, which is what happens as soon as you leave 4.1. Get the hell out of 4.1 as soon as you can. Get 4.3, 4.4, that's where all the action is. That's where all the good stuff is. I mean, it's worth going over. You look, whatever. It's exercises, it's practice. It just ain't my favorite problem. Looking for something on this closed interval. Any other requests or concerns anywhere? Requests, concerns?
I'm still on 4.1.
Yeah, okay, well catch up. I mean, we've learned a lot of stuff. I mean, you really need to be doing first derivative tests, concavity tests, inflection points. That's all 4.3, 4.4. That's where the action is. Okay. 4.3, yeah. Get out of 4.1. I mean, do 1 or 2 problems and move on. That's, again, some of you, I think maybe you have this idea that I got to finish this homework before I move to this homework. That's really, no. Sample this homework, sample this. Just do a sample of everything. Like you're at a bar, a breakfast bar or something. Take a little sample of everything. You don't have to finish all these eggs before you try the bacon. Sample this homework, man. You got a big, long homework list, and nobody's making you do it. Nobody's grading it. So my best advice is sample as much as you can. Yeah. You don't have to really finish anything. Hey, so for a while I skipped that 4.2, and now then I went and I talked about it and I assigned a couple problems. Let me just try one here. In 4.2, I guess I can do. I don't know, like number 13. So I'm in 4.2, and I'm going to do this number 13, and it give me a function. And it is I actually assigned this one to you, x to the 2/3 minus 1. Hey, again, I'm working on a closed interval. I'm working on this interval -8 to 8. But this time, what I'm trying to do is I'm trying to learn about this Rawls Theorem. Now, I kind of remember what it said. I introduced it last Friday. It's in the notes, maybe it's in the book. What does Rawls Theorem say? First of all, it says that the function has to be continuous from -8 to 8. By the way, hang on just a second. Let's see what these directions say. These directions say, determine whether Rawls' theorem can be applied to this function on this interval. If it can be applied, then find all the values C such that Rawls' theorem says that f prime of C might equal 0. Okay, let's try it. So Rawls' theorem says it's got to be continuous. Right, it's discontinuous if it's undefined, or if we got some issues. Listen, this is a cube root. You got no issues with cube roots. This is a cube root. Cube root has no undefined problems. Square roots and fourth roots might have some problems. And denominators have problems, right? I'm thinking about undefined problems. This is a nice cube root. I don't think this has any problems. So is it continuous on the interval -8 to 8? I think so. So pass that test. All right, so guess what? It also had to be differentiable. It had to be differentiable. Well, that means, do you know what that means? The derivative is defined. The derivative is defined. And if it's non-differentiable, the derivative is undefined. So now I'm not looking at the function. See, I guess for continuity, you're looking to see if the function's defined or not. For differentiability, you're looking to see if the derivative is defined or not. So now I need a damn derivative. All right, derivative. It's not that hard. It's not that hard. 2/3 x to the -1/3, which is actually 2/3 x to the 1/3. And I can tell you right now, this is undefined when x is 0. So it's undefined at x equals 0, which means it's not differentiable. My function is non-differentiable. The derivative is, hang on, the derivative is undefined. The derivative is undefined when x equals 0. That means the function is non-differentiable at x equals 0. According to Rawls Theorem, it had to be continuous and it had to be differentiable from -8 to 8. It was supposed to be differentiable from -8 to 8, not including the endpoints. So mine's not, right? Mine's not. It's not differentiable right in the middle there at 0. So it's supposed to be differentiable from -8 to 8, not including the negative. So it's non-different. So no, just stop. Rawls theorem cannot be applied. You gotta know what Rawls theorem says. It says that. It says it's got to be continuous. It says it's going to be. So I'm done. Maybe this was a bad example, but it's actually an example of where Rawls theorem fails. You can't even apply Rawls theorem. It's not going to be true. There is no C values. Are you guys confused? You want to do another one? Okay, let's do another. Let's do one I didn't assign. Let's do 17. 17 is this function. F of x is sine x. And they says I'm working from 0 to 2 pi. All right, so you ready for this? In order to do Rawls theorem, it's got to be continuous from 0 to 2 pi. It's also got to be differentiable from 0 to 2 pi. So is it continuous? It's a sine function, you guys. Is it continuous from 0 to 2 pi? Yeah. And it's a sine function. Is he differentiable? He is. And let's see. I guess I could take a look at his derivative. What's his derivative? Cosine. Does cosine have any undefined issues or any problems? Or no, it doesn't. It does not. So it doesn't take me long. I'm looking for bad places. I'm looking for undefined places to disprove these things. But I couldn't find any. It is continuous. It is differentiable. So now I should be able to go for the conclusion of Rawls theorem. What the hell was the conclusion of Rawls theorem? The conclusion was there is a C. There is at least one number C. There is at least a number called C that lives in there. It lives in 0 to 2 pi, where the derivative is 0. Where the derivative is 0. Oh, wait, there was some, wait. There was another piece of Rawls theorem. Hang on.
Yeah.
Right, I never got to the third piece. Shit. All right, it's got to be continuous. It's got to be differentiable. The other thing is, f of this endpoint is supposed to equal f of this endpoint, and not our, yeah, they're just supposed to equal each other. That's what they are. So is that true? Let me think. What is the sine? What is the sine of 0?
0.
Bless you. The sine of 0 is 0. And what about the sine of 2 pi?
0.
The sine of 2 pi?
0.
Yeah, you're right. Okay, cool.
Yeah.
All right.
I was gonna ask.
Those are the 3 requirements, and then you say, okay, cool. Now I can do Rawls theorem. So there's guaranteed there's a C value somewhere in there where the derivative is 0. I had to meet those 3 requirements first. Okay, so what does this mean? To find this C value, it's where the derivative equals 0. Maybe I should,
Plug in 0 to 0.
well, right, set my derivative equal to 0 and look for these places. Okay, and by the way, I'm only working from 0 to 2 pi. When does cosine equal 0? Maybe now I'm thinking about my unit circle. Cosine is 0.
Pi over 2.
Yeah, 90 degrees, and which is pi over 2, and 270 degrees, or 3 pi over 2. And those are both in this interval. Remember they said there was at least one, but I just found 2 values. I mean, When does cosine equal 0? I mean, we're done here. Pi over 2 and 3 pi over 2. So we found the values guaranteed by Rawls' theorem. I mean, in a way, what am I doing? Taking the derivative and setting it equal to 0. That's all you're doing, except you got to make sure that you can use Rawls' theorem. You got to meet the criteria to use Rawls' theorem, so I had to discuss these things. I passed all these 3 tests, and so, okay, now I'm allowed to do Rawls' theorem, which is look for when the derivative is 0. Remember, this one didn't pass Rawls' theorem. It didn't pass the test, right? And by the way, just look at it now. Just pretend if you were looking at this and you wanted to know when this derivative was 0, when is this derivative 0?
No.
It doesn't equal, this derivative doesn't equal 0. But I thought Rawls' theorem guaranteed it. Well, yeah, only if you pass the criteria, right? Then Rawls' theorem guarantees it. So, right, so this remember this one failed. And so it's not guaranteed and it doesn't exist, right? Yes?
How many Rawls theorem questions are going to be on the quiz?
I don't know. Yeah. Well, you want to choose, is it too confusing? You just give it. Or maybe it's too easy, you like it. You want a couple. I don't know. What that question implies is he doesn't want any or he wants a lot. So I don't know. Or maybe just, yeah. Anyway, I don't know. Or he's just curious. Right. I don't know. I never know until I do these things. The mean value theorem is another one. Let's just talk about it real quick. I mean, I introduced these and I never did any problems. So now today I'm doing a couple problems. All I did the other day was write down these theorems. Yeah, that one looks kind of fun. I told you to do 48. Maybe I'll do 48 with you here. 48 says this. I'm in 4.2, and this is about the mean value theorem. They give me a function, e to the negative 3x, and I'm working on this interval 0 to 2. All right, let's see. This is the mean value theorem. Here's what it says real quick. Again, without me writing the whole thing up here. What it says is it better be continuous on that interval. So I'll check that. It's got to be continuous from 0 to 2. It's got to be differentiable from 0 to 2. That's what it's got to be. What else did the mean value theorem say? Did it say, it didn't say this, did it? No, it didn't say that.
No.
It didn't have that criteria. This is special for Rawls' theorem. That might have been all it said, right?
Yeah, that's all.
That's all it says. So if that's true, then here's what's guaranteed. What they guarantee then, if you pass this, by the way, do you pass this? Look, this is an E function. Maybe you realize E functions are beautiful continuous functions. They got no problems. So from 0 to 2, yes, it's continuous. Just because I know what it looks like and I know it's got no issues. I also know his derivative is real easy. Let's go ahead and do it. What's his derivative? Good. He said e to the negative 3x times negative 3 is what he said, because that's the chain rule. So there's my derivative. My derivative has no issues anywhere. It's not undefined or anything, so that means this function is differentiable. So I think I just passed these 2 tests just sort of by inspection, looking for undefined places and not finding any, you know? So now what the hell does mean value theorem say? It says this, you're guaranteed that there's a C value. Again, you're guaranteed to have this C value. There is a C such that this happens. F prime of C equals F of B minus F of A all over B minus A. That's what it says. So, I wonder what I could do. What could I do? Well, I'm going to look for this c. So I'm going to try to find this c value. So right now it's just an unknown x, let's say. So do I have f prime? Yeah, there's my f prime of x. Negative 3 e to the negative 3x. That's my f prime of an unknown x. Now that I'm going to set this equal to this. What is this? What is this? This is f of b. And by the way, there's your a and b, right, you guys?
Right.
So f of b means take 2 and plug it in the function. If I take a 2 and plug it in the function, I get e to the negative 6 minus, plug a 0 in that function. You know what you get when you plug a 0 in that function?
1.
Thank you. E to the 0, which is 1. All over the b minus the a. The b minus the a is the 2 minus 0. 2 minus 0. 2. Okay, so they're saying that somewhere, look for this c, find this c, somewhere the slope equals that. Find the place where the slope equals that. Let me show you this. Hang on. I mean, I got some algebra to crank out now. What I was going to do, though, before I did that, was show you this visually. Here's a picture of this function. That's a 1. From 0 to 2. When I plug in a 2, what did I get when I plugged in a 2, you guys? What did I get? 1? No, when I plugged in a 2, what did I get?
Oh, yeah, you didn't.
Yeah, so this is a teeny little number. In fact, it's teenier than it looks, but it's e to the negative 6. In fact, maybe I should, hang on, let me make this a little more drastic. I'm sorry. Just trying to make it a little more drastic here. All right, now here's visually, here's what this mean value theorem is saying. It's saying, calculate this slope, which is just an average slope between those two y's and those two x's. That's between these 2 points. Calculate that. That's a slope. And then they're saying there is a c value somewhere in there where the function has that slope, where the derivative is equal to that number. Watch. There's a c value somewhere in here. There's a c value where the tangent line has that slope. That's what the mean value theorem says. Visually. There is a place. You can find a place that has that slope. So I can find that place if I solve for x here. And solve for this x. And this x will be the c. It'll be the c guaranteed by the theorem. All right, so now it's algebra. I'll move over here where I got a little room. This is negative 3 e to the negative 3x. What is this? E to the negative 6 minus 1 all over 2. I'm just going to keep it like that. Look. So how do I solve for x? Divide by a negative 3. Is that okay with you? Yeah. Divide by a negative 3. Huh. Jesus, you know what to do now? Take the ln of both sides. The ln will kill this e. The ln will just be a big nasty ln here. Divide by negative 3. There's your answer. Dude, it's probably the craziest answer you've ever seen. X is this answer. The natural log of e to the negative 6 minus 1 all over negative 6. That whole thing divided by negative 3. Is that what I'm saying? That's what I'm saying. Hey, can somebody punch that in your calculator successfully? You get an automatic A in the class if you can type that in your calculator. No, I'm kidding. I'm kidding.
That's on video.
That's on video. Oh, no.
I got it.
My point is, it might be a challenge for you to type this in your calculator. Good luck. Embed your parentheses well, and good luck. But this is some little C value is what this is. This is going to be the answer C, where it's going to be somewhere between 0 and 2. There's a place here where we have this slope. That's the point of the mean value theorem.
Yeah, I got 0.598.
What did you call it?
I don't know if it's right. I got 0.598.
0.598.
Yeah, but I don't know if it's right.
Anybody agree? She agrees.
That's what I got.
Did you get it?
He agrees.
Oh.
All right. Cool. So this is the C value guaranteed by the theorem.
Yeah.
The place where we have the slope, that there is a C, where the slope is this number, and this is the process we go through to find it. You can try. I only assigned 5 or 6 problems. You could try those. You could try one. You could try a couple extra if you feel like you need a little more practice with this stuff. You might. I mean, you could try a couple extra right there in the vicinity of what I assigned. Okay. That's enough of that. So I feel like in 4.3 and 4.4, that's kind of what I was practicing last week. I was doing first derivative tests. I was looking for inflection points a little bit. I was doing more. I was more there, and that's more important. That 4.3 and 4.4. Do you have any? And then we found a couple unique questions last class. We did a couple up in the 70s that were kind of good. All right, I'll tell you what. Let's try this one. So I went to 4.4. I'm just doing homework today, I guess, unless I might have some other cool thoughts for you. I just went to 4.4 and found this great question, number 15. 15, 1/2 x to the 4th plus 2x cubed. The function is 1/2 x to the 4th plus 2x cubed. So this is a function. It's number 15 in 4.4. And what are you supposed to do? Everything. So if on a test, I might just say, do everything.
Well,
No. You know what that means? It means find mins and maxes. Okay, so what does that mean? You're going to take the derivative, you're going to find your critical numbers, you're going to put them on a number line, do a first derivative test, and see if they're mins and maxes. Did you hear all that? Okay, now that's half of the problem. Now, then you're going to do a second derivative, set it equal to 0, look for inflection points. Or possible inflection points. You're going to put them on another number line and test for concavity. And then you're done. That's a complete thorough analysis of a function. That's worth it. That's a question or two on a test or this quiz Friday. But they're time-consuming kind of problems. You know what I mean?
Yeah.
So I can't ask you 12 of these. I can ask you 1 or 2, and they're worth kind of a lot of points. But do everything. So I'm going to let you get started. I'm going to hit pause real quick.